Welcome to week 9 for PLC2 shift registers. So, couple things, being that this is virtual, I hope you're all staying safe. We're definitely in quarantine and not having very much fun. With that said, I encourage you to pay attention here. This is going to be kind of complicated, so if you need that little explanation, I'll try to provide it. Otherwise, quite a bit of it is in the book. Okay, so here we go. A couple of issues. So saving on the virtual machines could be an issue. I hope that you've figured out how to let it access your thumb drive. And I want to be sure you verify that they're being saved there and that you can reopen them. The HMI program might not be saved, and it might be hard for you to re-access it. The bummer is there that you have to recreate that each time. I'll try and keep the HMI IO simple so that if you do need to create that, it won't take very long. Do you need to set up the emulate each time? Well, if you open up your prior project and then I think you just broom out the ladder logic, I think that it'll keep the IO configuration where you install the 1756 module, and then your emulate, I think it'll keep it intact, I hope. Otherwise, you're going to get good at setting up that emulate very quickly each time. Okay. Timeline. We're going to stick to the timeline that we've been. So on Tuesday, your homework is due. So the homework for the coming week will be on Tuesday. On Thursday, the lab is due and then a quiz. So, and that's from prior. And then either Thursday or Friday, I'll release the next lecture video. I'd like you to watch the video and see if there's information there that you can gain from it. You don't have to take any notes or anything, but it's probably help you pass the test. Try to stay caught up. I've been fielding hundreds, if not thousands, of emails. I try to get back with you just as soon as I can. So email, and I'll try and stay up with you. Okay. And some of you guys don't sleep very much because I get emails all the way into the middle of the night, and I still try and get back to you. So can't promise if you shoot me an email at 3 o'clock in the morning if I'm going to get back to you, but I guess you can try. So let's take a look at the review from the number systems. We did not have a thumb wheel. Okay. The thumb wheel would have allowed us to work with a double word dent and bring that into the PLC. Otherwise, how do you bring a word in? In the past, we've just been using digital, like push buttons, they're zeros or ones, but to bring in a word that we want to manipulate, well, then that becomes difficult without a thumb wheel. So what we used was a HMI. And an HMI, we were able to bring that number in and modify it and compare it and do all kinds of stuff. Another good example might be a barcode scanner in a system that scans a number, okay? But we were working with a thumb wheel. The thumb wheel was 9999 decimal, and then that would bring it in. So just to recap how the thumb wheel works, you have a BCD to 7-segment decoder. Here's on the output. You get 4 inputs per display, okay? Because there's a 16-put input module, so you get 16 divided by 4, that's 4. So you would get 4 LED displays, and ours were up to 9,999. So if you outputted something here like if you had a 1 here and then 0, 0, 0, well, that is 1. And it would, the BCD to segment coder would turn that 1 into something the segment could display, which would be turn on light B here and light C here. So B and C would come on. So we were using the PLC to do some of this, okay? So once again, our thumb wheel had essentially 4 of these on it so that we could go up to 9999. If we wanted 9, by the way, we would turn on the input, looks like the 1, so we'd put on this light on the input module, and we turn on this light on the input module, because 8 plus 1 is 9. Here they're showing 8, so they only have the 8 on. So this input module would be reading input 0, 1, 2, input 3 is being on, okay? So that's the way that that thumb wheel was being read into the input module, okay? And on the output, it's very similar. You have the encoder pushing numbers out to a digital display. And if we took in A and D, which would be 9, A and D here, because we have the 1s, 2, 4s, 8. 8 and 1 is 9. This encoder would push out to turn on all these lights. So it'd be a 9, which would be this, A, F, G. So it'd be D, C, B, A, F, G. E would not be on, and it's not. It's a 0 there to indicate 9. So that's kind of how the thumb wheel was working, okay? Now, thumb wheels, set the thumb wheel to 9. What do we get? We get inputs 0 and 3 to come on, because in this code right here, we only have one thumb wheel. We get the 1 here and the 8 here, which is input 0. There's input 1, input 2, input 3. So input 0 and input 3 are on, and that signifies 9. If we wanted 99, then this would be 1001, 99, okay? So the BCD word, the 16-bit input module brings in that word, whether it was this word or it was 10001 for 99 or whatever word you got there, brings in the word. And the output module returns that word so that the 7-segment display could handle it. You needed BCD to decimal conversion needed in order to match the thumb wheel, okay? And we're using a PLC. There's solid-state circuits that can be used for this function instead of a PLC, but the thumb wheel was a way to bring recipes into the PLC so that we could change the number of chocolate chips we wanted to put into the mix, or change how long something occurred, a timing operation. Once again, the HMI seems to probably be a better way to do that. So the tag can be viewed by different number system formats. So we went and we looked at it, and I showed you how to change the tag radix so that you could take that number in and kind of, I made a little tag called math or something, and I just used the tag radix to change the number format, and it automatically converted it for me, okay? Move and compare. You need to be aware of the data types, dent, int, boolean, etc. The data types need to match, okay? So I have here demonstrate a move of a dent to assign it. So I don't have this here, but you can imagine that if you moved a 32-bit word into a 16-bit word, well then 16 of the bits are going to get truncated, okay? Or it might not let you do this at all depending on what you're trying to do, okay? So just be aware that you have to, if you're going to move or compare and do some stuff, yeah, this might not even work, that you want the data types to match. Try and move a dent into a Boolean. It's not going to work, okay? When you divide, sorry, I wanted to show dividing of dent and these things. It's going to do some truncation, and that's what the calculator showed you, and that's what the lab explained, okay? So, calculator. My solution is on the link here. It's pretty involved. I go and I demonstrate how to simulate that thumb wheel in, and it's involved. I want you to watch this video and fully understand everything that I'm talking about with a calculator, because this is gonna be what we're gonna see for the class for the next couple of weeks. Okay, so watch the video, understand it, and then come on back. Okay, welcome back. So we had some system information and states bits that we talked about. And unless you were simulating the thumb wheel like I did, you probably weren't getting your status bits to come true. For example, this is my status bit for scan. If you put a contact right here, that contact would close on the first scan of the once you put the processor into run mode. That'd be the only time it would close. Okay, but there are other types of status bits. They're not as prevalent in logics as you would find on a SLC 500 or a PLC 5. Okay, because we can manage our data and schedule a different way to get a lot of things going on. So my calculator example is here. So your PLC answer and your LED answer, unless you were pushing out that word using the TOD like I did, FRD TOD, you probably were mostly interested in the PLC right here. Okay, so let's just look at a couple of things real quick. 36 divided by 72 right there. Well, that's a half. I know it's a half. But my PLC and my LED are giving me 0 because this is an integer, okay, calculation. And there's no, anything different than a whole number. There's no fractions or decimals or anything like that. So it gets truncated back to 0, okay? I think there's another, more divides here. 149 divided by 123 right here. Well, that's 1.1 or 1.22 or something like that. But we get an answer of 1 because we need the whole numbers of the integers. It's not going to give us 1.2, okay? So hopefully your calculator answers that you sent to me look something like that. Shift registers. These are very complicated. It's all out of the book. If you're a good book learner, go for it. But otherwise, I'll try and explain them here. Please listen carefully, and you'll want to watch the videos. And please email me any questions. I'll try to get right back to you. So the shift register allows shifting of bits. So they're shifted serially. So from left to left to left to left to left to left, or to right to right to right to right, through an array in an orderly fashion. And it's used to simulate the movement or track the flow of parts and information. So what they got here looks like they got a barcode scanner or some kind of a scanner here. Probably not a barcode. Just indicating whether that item is here or not. Probably maybe putting a 1 or 0 in there. Okay, we're going to do some part tracking like that. So the sensor drives the data to detect the presence of a carton in this case. A 1 indicates that there's a carton there, and a 0 means that there isn't. So this sensor right here apparently is going to trip every time a carton comes in here. So if there was a carton here, we'd get a 1, a 1, a 1, a 1, a 1. And if there wasn't, we would get a 0 in there, a 0, 0, then maybe there'd be a carton again, a 1, a 1, a 1. So we're basically building up a word, a 16 or 32-bit word that's 1s and 0s, and that tells me if there's cartons on there, okay? The solution to the labs are described in the textbook. So a pulse or a clock causes it to shift. So you need something to trigger this, okay? You could use, like in the previous example, maybe this was moving down at a steady rate, and every 1 second this thing knew that it was supposed to determine if there was a carton there. So that would be a clock that would cause the shift to occur. Or if there was a limit switch on the conveyor here or something, that when the conveyor reached this point, there was supposed to be something on the conveyor, okay? So that would be a pulse. So somehow you're going to get this clock to shift, and here's my original position, and then this shifted. So this 1, you see there's 0 here, this 1 fell off the array. It's gone. This 0 moved over, and this 0 moved over, and this 1 moved over. So you see, if I get rid of this 1, my last numbers are 0, 0, 1, and here 0, 0, 1. So this whole register is shifting right. Okay, next time I get a little data, it shifts right again. It looks like this 0 falls off and goes away, it's gone. And this 0 moves one slot over, the 1 moves. And so it's just shifting the whole word, and it's bringing in the new value. Whether the carton is there, it puts a 1 there, and if the carton isn't there, it puts a 0 there. Okay, so types of shift registers. There's BitShift right, where it shifts in the right direction, and then the least significant bit falls off and it's gone. Or it's left. You can shift left, where the most significant bit here falls off and it's gone. And we keep pushing 0s and 1s, and then those bits shift orderly through the word. Okay, bit shift left, that's where you're going to find it. That's what it's going to look like, BSL. And then bit shift right is going to be right there, BSR. Okay, and you're going to need it to look like this. What's shown in the book is how it would look in a SLC 500. Okay, so a file, address of the bit array. The file is replaced by an array here. So we would have a bit shift array. So that's just a tag called bit shift array. We'll call your tag whatever you want, and it's going to contain the word. Okay, you are going to need a control, which we'll talk about in a minute, and then we're going to talk about your source bit. The source bit is the 0 or the 1 that is getting moved into the array. So apparently this is shifting left. So if the light's on, it pushes a 1 in there. If the light is off, it pushes a 0 in there. And I've got an example that I will show you there. The bit shift left needs a control, so you can call that control whatever you want, Dorito, whatever you want. You can call this array, Dorito array, whatever. But it needs a control. So a control is a predefined instruction for that, or tag. And when you name it and you make it a control right here, well, then it comes with like a done bit, an enable bit, and some of the things like this, and it tells you what position it's at. So this is predefined to allow you to access the status of the BSL or the BS right, depending on what location it's at. So this kind of keeps track of the location of that array. Okay, so you have a spray painting handout right here, and it looks like let's see what's going on here. It looks like there's a hanger here, and something's coming through here to get spray painted. Okay, so what it does is it looks like it's going to make a limit switch, and then that limit switch is going to determine part entry up. So limit switch 2 is going to, I think, sense limit switch 1. So when the system, the conveyor, hits limit switch 2, limit switch 1 checks to see if there's a part there, and then it's going to do a shift, and so the next part will come in, and if there's a part there, limit switch 2 will tell you a part, it'll put a 1 in there. Limit switch 2 will tell you if there's a part there, put a 0 or 1 there. So you're going to get this word 1 0 1 1 1 0 whatever. Okay, and then when it comes down the line here, we're going to use that word to turn on spray guns at different locations. Okay, so as we take a look at this ladder logic, you're going to want to look at this conveyor system here. So what is happening? Your limit switch 1 is your pulse. So you could either do it once again with a clock pulse. You can use a clock that it pulses every second or every half second or something, or you could use a conveyor location or something to do it. So let's just look here again. It looks like the hanger is causing this to shift left. Okay. The limit switch 2 looks like it's counting. Okay. and then my bit address is input 1, 2. So the second limit switch here. So once again, my hanger is my clock. That's causing every time limit switch 1 hits, the word shifts. Shift, 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 shift. And limit switch 2 not only counts, but it determines a 1 or a 0 depending on if there's something hanging in here. Okay? So limit switch 2. So if there's something hanging in there, when that pulse comes, it puts a 1 and then it shifts. And next time when when the conveyor makes it, if there's something in there or not, a 0 or a 1, it pushes that into the word and then moves on left. So pretty soon you get a word of 1, 1, 1, 0, 1, 0, 1, whatever, depending on if you have something in there. And this one is just counting an up-down counter to see how many are coming through. Okay. So once you have this word, you can use this word, and we'll see, to then turn on the spray gun or the top coat gun to spray if something is there. And I don't know if they're actually they are showing that here. So we are, in this case, once again, this is showing it's 500. That word of right here of input 1-2 of ones and zeros is being put into a file, a bit file, but you'll be putting yours into an array file because a tag, an array. So we've got this bit B3 here is 10111001 whatever. So as this rolls through, when it gets to this location, if for some reason I've got a 1 in bit 30, the 0 location, so there's 0, 1, 2, 3, 4, and the 5th location of that word, right? So my word could be 1, 0, 0, 0, 1. So 1, 0, 0, 0, 1, 0, 0, 0, 0. When it came through, this bit location, the gun would come on, and then it would shift and it would go off because it'd be a 0. And 5 would come on. The 5th bit right here is going to trigger the solenoid for that gun. So that's a lot of explanation. Take a look at it in the textbook and it explains it. We have manual load and unload. So this input right here, apparently in this system, a prox causes a bit shift left. Prox, 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 prox. This word is shifting this way. Boom, boom, boom. And what it's doing is it's taking the bit address from an input, status of an input, once again, input 1, 2. So apparently there's a second prox. So this carrier detection, the purpose of this is to shift. The purpose of this prox is to put zeros or ones into here, okay? So it takes 0, 1, shift, 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 keeps shifting every time this hits. So what happens when we get here is at an inspection, let's say we have to take something off the line and there'd be a 1 in the word. We could push the PB1 and it would unlatch output 4, 4. So it would push 0 in here because that's what unlatch does, is a 0. And then we could go down the line, and if we reworked it and we wanted to put it back in, we would push this push button right here, which would put a 1 back in, output 4-6. But then it would shift, 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 and then this goes off and it resets. So this is a way to push a 0 into your word, and then maybe a rework station push a 1 back in to keep track of that word. And as this goes, these lights are just going to kind of, because they are pushing this to the output module, these lights are just going to cascade down. This one would become lit, then this one would go off, and this one on, and this one off, this one on. These would just kind of cascade down there. Okay, so once again, I have a complicated example here of BitShift that you're going to want to watch, and you're really going to want to understand how this BitShift is working. Watch as many times as you want. Okay. WordShift operations. These are similar to the BitShift, except we're dealing with a file. Okay, so a file is a group of words. We're no longer looking at shifting a bit, we're looking at shifting a word, okay? And here's where we're talking about a barcode scanner. This barcode scanner is going to get a 16 or a 32-bit word, and we want to store it, okay? First in, first out. These are word shift operations. So the first in, first out, load and unload, okay? That's where these instructions are. And what they do is we create a stack. So two shift pulses are required, one to load it and one to unload it. So we're making a stack. So what I mean by making a stack, let's just think about a stack of plates. First in. So when I get a word in, let's call it a dinner plate, imagine it going on the counter. And then let's imagine you get in another plate and you set that plate on top of the next plate. So now you have 2 plates in your stack, and then 3 in your stack, and then 4, then 5, whatever. So you get this stack of plates. Well, which plate was part of the stack first? Well, it's the bottom plate. The bottom plate is where the stack started. The top plate was the last one in. The bottom plate was the first one in. So when you go to unload, you can unload the first one. So you would start by taking the plate out from the bottom, and then you would take the next plate out that's the new bottom, and then you would take the next plate out that is the new bottom. So you would kind of unload from the bottom. That's called first in, first out. You could also have first in, last out. So think about that. You got a stack of 5 plates. What was the plate that went on first? Well, it's the bottom plate. But if you're first in, last out, how do you do it? Well, you start unloading the plates from the top instead of unloading the plates from the bottom. So the book kind of explains that. First in, last out, first in, first out. So the FIFOs here, you're going to need a control as well. You are going to need a length, and you're going to notice that the length is going to need to be, here's important, 1 more than the stack that you want, because the last word gets chucked off into infinity and it's gone. So if you want to keep track of 5 numbers, you're going to need a length of 6. You're going to have a control, and the control is the predefined data. So FIFO, first in, unload, and first in, load and unload is what we got going right here. There's my control word, and then you have the enable, the done bit. So basically the done bit comes to 1. So when let's say you want to stack up 5 plates. You put 1 plate, then 2 little plates, 3, then 4, then 5. Once you got 5 plates in a stack, well, then that control gets done, and then you can know that your stack is done. At that point, maybe you want to use that done bit so that when a new plate comes on, you unload the plate off of the bottom. Maybe that means it's dry. So put a new plate on top, take one off the bottom, okay? So that's how this will be explained later. Data are indexed in this. So indexed in and out of the file. So apparently input A caused me to load. Input B would cause me to unload. So here we go. Data indexing towards the starting address of the file. 1 word with each false to true. So that is I would load this up this way, and if I wanted to unload it, it would start shifting this way. So if this was first in, 31 would be in, then the next one would be 53, then 146. So these would start stacking up every time I push the input. Where am I getting these numbers? I'm getting them from a location here. For some reason, 7N12's got all these items in here, and it keeps shifting through there. Okay, my source is 7N10. So when I go to unload them, well, it's first in, first out. So I'm going to take 31 off first, and then 53 moves up. This moves up. Everything moves up. Okay. Notice it says data exit from position 0 to the FIFO file on a false to true transition. So take a look at this in the book and be sure that you understand that. These are usually used for inventory control. You get a unique code on here. You want to take that code, you want to stack it up, and then as you ship it off, you want to remove it, you want to put it and store it someplace safe, and then you understand your data. Here's our last in, first out. That's kind of what I was explaining. It's in the book. We're going to do a little bit of last in, first out, but we're usually doing first in, first out. And here's your last in, first out that they talked about. The stack I was talking about, plates. So this was first in, or vertical storage. Okay, so this is opposite the plates. Take a look at this in the book and see if you understand. I was talking about stacking of plates. They were talking, this is going the other way for some reason. So there's my stacking operations, okay? And here's my last in, first out. It's in the book, and it just talks about the direction the word is flowing up to down and down to up. It's just a little bit different than what you would see in the other one. Okay, so that's a lot. But here's an example of a word shift. You will want to watch this video very closely and be sure you understand how the word shift is working. Okay, this explains it. So we have a quiz. It'll be an online quiz that will be released. And then for the lab right now, I would like you to complete parts A and C. This is a BitShift and that's a word shift. You really want to understand them. You want to email me. You can do a picture of your simulation and then email me the lab, and I will take a look at it. And I'm going to assign a more difficult bit and word shift assignment. So the goal is to really understand how all of this is working.